Hi, and welcome to another Hopper language video. This is from the language playlist, the Hopper language playlist, which describes the features of the Hopper language, which is a modern curly brace and semicolon language similar to Java or C Sharp, but without objects, and designed to run on small devices like 8-bit CPUs or microcontrollers. Today I'm going to be demonstrating a new feature that I've just recently added, which is records, a new structured type. And I'll be using the debugger on the microcontroller. I'm running on a Raspberry Pi Pico, actually on an Adafruit clone, but it's useful to use the debugger to show the features. I'm going to give the overview very quickly in the beginning, so you'll probably get most of what you need to know about records pretty quickly. And then it could go on for a while, and I wouldn't be surprised if it doesn't get viewed to the end by most. All right, so let's start our program. And since we're going to run on a microcontroller, in the debugger, we're going to want to use the serial console from the microcontroller to see what's going on. So to do that, I use this IO class, unit, and this serial console allows me to switch between using it for Windows or using it for the microcontroller just with one switch. So it's got a bunch of features here to be able to write to the serial and read from the serial port when I'm running on the microcontroller. So let's go back to that. So if I right click like that and then build it, F7 shortcut keys on the menus. Now I can start launch with the debugger. The screen tells me I moved into the debugger. And this black area on the right here is the serial connection to my Raspberry Pi Pico. So F10 to start the program, and now I'm going to F10 to step over right lin. And this code's executed on the Pi Pico, and it output hello world to the serial port. Okay, we got the general idea. Now let's go do some records. Alt F4, back to here. So most of the time, Hopper has, for most of the time, had anonymous structured types like this one here. So that's a list of strings. Or I can have a dictionary that's where the key is a string and the value is a uint, or I can make my value be a list of strings, so etc. etc. So you can build these sort of structured types, but they're anonymous types, and it's duck typing. So to be able to assign one to the other, if it has the same type signature, then it's valid. There's also arrays and there's strings. But go and look elsewhere on the playlist for how those are defined. So I managed to build this editor, the debugger, the compiler, preprocessor, compiler, optimizer, code generator, disassembler, about 80,000 lines of Hopper source code without actually needing a named type that's structured. Up to this point, there've been 3 named types. So how can I easily find there? Yes. So one of the name types is flags, which is like enumerations. Another name type is actually enumerations. And then the third name type is when you give the definition of a callback. So like one of those uses source library. I don't really need to use the MCU, the microcontroller library, because I'm not using any features that only exist on the microcontroller. But if I had, and then we go and look at GPIO pins, is this where they are? There's some callback functionality. Where is it? Well, it'll be in the web class for sure. Timeout will have callback. So there's a delegate type. So this is a named type. Which is the delegate type. So delegates, enumerations, and flags up to this point have been the only named types. So now I've added a structured name type, the first structured name type. And it's called a record, and it's based on how Turbo Pascal did records. So like a struct in C, for example, and then we give it a name like my record, and then we give it members, and just like everywhere else in Hopper, you first put the type and then you put the name of your identifier, so it's like that. We can declare a local one like that, and then we can assign values to our string value, and our uint is going to be a uint like that. So let's build that at 7. And it's up, and now we go F5 to launch the debugger. So it's uploaded. If you look at the bottom of the screen, it is successfully uploaded to the device, and then F10 to step into it. So let's create our record. And when I look at my record here in the debug output, it's basically uninitialized. So it does lazy initialization, and there's a good reason for that. And then as soon as I F10 to assign the string, it should also initialize the uint. So this uint should also go to 0. There we go. So as soon as you first use the record, it initializes all the fields. And now we'll get the 42 into the other field. There we go. And yeah, I can double click on these to show them in another window. Okay, so that's the basic gist of a record and how you would create one. Let's go, and we can add other types of into our record. So I can have an enumeration like that, and then I can put my enumeration type in here and do add. So the default value is always the 0 value, so it'll be the 0 value if I don't initialize it. And that's true everywhere in Hopper. If you don't initialize something, it gets the first value of the 0 value. So false for Booleans, the first value of an enumeration, empty string for strings, 0 for numerics. So let's make it the v2. There we go. So we've got a second type. We can also put structured types in here, and these are these anonymous types. So if we make a list of bytes like that, and we would initialize it by making a list of bytes here. And let's how do I want to do that? Okay, so in 1, so we make a list, and then we'll assign that in there. So you put structured types in like lists or dictionaries, and you can nest them. So, all the things that make sense logically you could do with it. Okay, there we go. We can check if it's working. We can say if my value is 42, then then my string value. Let's do that. Okay, and we'll load that up into the device and hit F5, and my string value got printed. And after it ran the whole program, it reset to the beginning again. So now I can run it again by single stepping through. So I'm building my list. There's my list, 1, 2, 3 on the right there. Call stack and locals here. And if I keep stepping, assign my 52. Assign my enum value. So my enum value is now assigned. My bytes are empty. It's an empty list right now. The default initial, and then if I do that, my bytes are now 1, 2, 3. And now it's going to check if my uint is 42, and it is, and then it's going to print the string value again. Just ran the program again. Okay. That's the basic gist of it. So you could do this with dictionaries. You can do dictionaries of dictionaries. You can build a hierarchy of types this way. One other interesting example let's do another one here. So a very common thing you might want to do is, build a structured, not a regular list, but sort of a structured list. So you can put in here string name and chain next, like that. So linked list, even though list is really a linked list, but you can make your own manual linked list this way. And you can get into trouble doing this sort of thing by making circular lists, but the garbage collector can deal with it all, because if it's not referenced from the stack, then it gets collected, because the stack is the only way you can reach objects. Okay, so let's have a look at that idea. So we can start building our list. Let's get rid of all of this by declaring front. So that's going to be our reference to get to our list. And then do a for uint I equals 0, I less than 4, I plus plus. Inside here, we're going to make another one. We're going to make our current elements. We're going to set current name to link I to string, that. And then we're going to set current next to our front. So we're building the list in reverse, and then we're going to set front to current. So I think you can see what that's doing. Makes sense. All right. So we could just run that and then put a breakpoint down here somewhere. Let's restart that. So we're building this list link where next is pointing to link 1 and next is pointing to link 2. Okay, kind of tricky to see how. Well, we could just walk it. So in the same way, we can make a disposable one here. Walk equals front. Like that. So we're initializing it chalk. Like the error message at the bottom, chalk, as opposed to chain. Okay, let's try that again. Chain, not chalk. Chain and walk. Funny what the brain does. Okay, so now we can use the last one in the list, which was the first one here, front, will have an empty, I never initialized its values, so if walk dot name is not empty. That means I've got one of the ones I created over here because name's not empty. And then I can say walk equals walk dot next, but before I do that, I probably want to so let's build that F7. Not an uppercase. Where did I put the uppercase? I'll talk about uppercase in a second. So there we go. We've walked it and it comes out backwards. So when it steps through here, it's going through the list backwards. So you can, do this sort of self-referential thing inside records. Now, about the casing, if my record type starts with an uppercase C, that's what, just like the Go language, uppercase means public and lowercase means private. So this means you can see this record outside from other units. And then the same is true of the members. So you can have a public record, but you can have private members in it, or you can have some of them be public and some of them be private. And that's how, so you can encapsulate your stuff into just the unit you're working into and only expose the bits to the outside world that you're confident on can change. All right, what else? You can make a, I could have made my, you could make a global, you can make global types like that too. So we can make front be a global like that. And we could make it uppercase and then to be visible from outside here too. So if I did that and then I put front end like that, that'll still do the same thing. Variable, ooh, yes, you can't do that. You can't make a variable public like that. But you can, I wonder if that'll work. Global variables have to be private to a unit, but properties can be public. Let's see how well that does. I got a brace wrong. There it is. Okay, let's go. So it's initializing from front here, which is this one, through the property, the public property, which should be empty. And if it does that, let's see if we get the same result. We do. So I've exposed a public property called front, which exposes a private global variable. So outside of this, if this was a unit, not the main program, you could use that from outside. So that's how public and private works in Hopper. Anyway, and it works with the members as well. So I think that's enough about records for now. Brand new features, so if anyone uses it and has issues with it of some kind, please let me know. I've been testing it pretty thoroughly with lots of variations and permutations on this. But I wouldn't be surprised if there's still an issue or two in it. It's not as stable as the rest of the system because it's brand new. Anyhow, thank you for watching. And I look forward to your comments. I'll put a playlist to the rest of the languages videos at the end of this, and I'll put a link to the latest release in the description. I'll also add the playlist that shows you how to get that release up and running in less than 5 minutes on your Windows machine.